Welcome to lecture 810, the 10th lecture from VLSI design from chapter number 8. We are studying VLSI design, and today we'll continue studying path delays. In our last lecture we talked about a chain of inverters where the following inverters are greater in size compared to the preceding inverter by a factor s, where s was computed to minimize this time delay tau d. A mathematical operation was performed, and the final result was that if we put s is equal to small e, we get the minimum time delay tau d. And we also rewrote this expression. This expression was rewritten to take n on the left hand side and everything else on the right hand side. The CL is s to the nc. The final load driven by the final inverter is s to the n times c, where c is the minimum capacitance, that is the input capacitance of this inverter. And the general expression for the total delay was n times the scaling factor times the rise or fall time delay of this first transistor, of this first gate NOT. Right, after we have done this recap, in this lecture we will start from the fact that we derived, after deriving deriving that s is equal to e, we know that log of s is 1. So n can be written as, at the expression for n that we wrote in our last lecture is this. So the denominator of this expression is log of s. If we put log of s, means if we put e here, log of e, which is 1. So the expression for n is log of CL over C, right? And the time delay, the total time delay, is ns times the time constant tau. So the tau d, the chain time constant of the chain, is log of CL over C1, because the value of n is now this, times s, where s is e, we computed in last lecture, times the same tau. Right, after completing this whole theory, now we are ready to solve an example where CL is given to be 10 picofarad. For this chain, CL is given to be 10 picofarad, and see the minimum input capacitance of this first NOT gate is 20 femtofarad, where femto is 10 to the minus 15, pico is 10 to the minus 12. We need to find n, the number of stages, to minimize tau d, exact value of s, and the values of beta, the device transconductance, right? In order to find the exact value of n, that the value of n that computes, that ensures minimum delay, is that we put in this expression the value of CL and C. So n is log of CL. CL is 10 pico, means 10 to the minus 12, over this is 20 femto, which is 20 times 10 to the minus 15. So it comes out to be log of 500, which is equal to 6.21. So it doesn't come out to be an integer, where the number of stages have to be an integer. It can either be 5 or 6 or 7. So let's assume it to be 6, because we cannot have 6.2 stages. Stages are either 6 or 7. number of stages are either 6 or 7. So once we have computed this n and we have done a small approximation where we have written this 6.21 as 6, now the exact value of s would be a bit different than e. How to compute the exact value of s? From this expression that we wrote in our last lecture, s to the nc, we can rewrite this expression to find the exact value of s. It can be written as CL over C is s to the n, and s can be taking the nth square root on both sides. This is CL over C to the 1 over n, and this comes out to be, if you put the value of CL 10 pico, C 20 femto, 1 over 6, this is 10 pico over 20 femto to the 1 over 6, the answer is 2.82. So the new scaling factor in this chain, after we have done this approximation, is not exactly equal to e, because small e is 2.71218. It's a bit higher than that. This is the new scaling factor after this approximation. So the last thing we have to compute is the set of betas. We know that betas would be increasing as we go down the chain. For the first knot, this is 1. For the second, this is 1. For the second, this is s. This is s squared, and for the last, this is s to the n minus 1. So what are the new scaling factors? 1 or beta, because beta is proportional to m, because m is directly proportional to aspect ratio, and we know that beta is kappa times aspect ratio. So this leaves m directly proportional to beta. So here we have beta 1, here we have beta, let's call it beta 2, let's call it beta 1. Beta 2 is s times beta 1, beta 3 is s squared times beta 1, and finally, since we have 6 stages, what would be the 6th beta? Here we have, in this case, we have 6 stages. So the last is s to the 5, where m is s to the 5. So the first beta is beta 1, the second beta, beta 2, is s times beta 1, means 2.82 times beta 1. Beta 3 is 2.82 squared times beta 1, and finally beta 6 is 2.82 to the 5 times beta 1. So that's all for today. We have studied how to, up till now we have studied how to minimize chain delays using a mathematical technique, and once we have done an approximation in a certain case, we computed a new value for the scaling factor and have derived the new device transconductance values for this increasing value of chain, for this chain where m's are increasing at every step. and for this particular example we have 6 stages, but in another example we may have different number of stages. In this course, or in this chapter number 8, we will keep on studying more about chain delays. Thank you.